Hello, and welcome to the University of Waterloo Robotics Team. Over the past year, our team has worked incredibly hard to develop our newly designed Mars rover robot, Rocky. In this video, we are excited to showcase our rover's capabilities and present our team's 2023 System Acceptance Review submission.
This year's rover features a brand new mobility platform. Our new drivetrain utilizes 6 wheels coupled to a rocker bogie suspension and differential bar. This allows us to keep our rover chassis level and maintain 4 points of contact with the ground through the variety of severe terrain we can expect to encounter in the extreme retrieval and delivery missions. Each wheel is independently driven by a brushless DC motor and planetary gearbox. 12-inch balloon tires are used to absorb collision impacts and maintain the traction on uneven terrain. During the retrieval and delivery mission, our rover will deploy with our new 6 degree of freedom arm. We have carefully designed our arm linkages to move mass towards pivot points and have switched from brushed to brushless motors to drive our arm joints in an effort to increase maximum arm payload. Each arm joint is driven by a powerful brushless DC motor and a combination of timing belts, planetary or harmonic gearboxes, and custom gear trains, and should be well equipped to handle heavier payloads on the field.
Each ARM actuator features pre-reduction Hall sensors and post-reduction absolute high-precision magnetic encoders. Our encoders and motors all interface with O-Drive brushless DC motor controllers to allow our operators to utilize open-loop position control, velocity control, ramped velocity control, and torque control on each joint. In addition to lower-level control modes, we also implemented a Cartesian controller to manipulate the end effector with higher precision. The arm will be controlled by an inverse kinematic solver generated by MoveIt API and will interface to joysticks and buttons for teleoperation. At the end of our arm, our newly designed end effector features compliant rubber pads to improve gripping capabilities on unique shapes. The end effector is driven by a non-back drivable lead screw to ensure that items picked up by the end effector will stay within its grasp. Additionally, a wrist-mounted camera is located at the base of the end effector to provide operators with a wider field of view of the arm to line up high-precision tasks.
To support our new drivetrain and arm, we have completely revamped our electrical architecture. The rover is powered by a 48-volt lithium-ion battery which powers the rover through a BMS system. Our newly designed power distribution board distributes 48 volts to the drivetrain and reduces the battery voltage to 17 and 5-volt rails to support the sensors, motors, and actuators throughout the rover. External to the power distribution board, a 24-volt rail is produced using a high-power buck converter which then powers the arm motors. An e-stop is connected to the side of the chassis to allow for emergency interventions if a system failure is observed.
This year's rover also features a new science mechanism. An elevator-mounted sensor head will be used to elevate prospective soil deposits prior to sample inspection by measuring CO2 level, temperature, and moisture. If a sample is promising, the science mechanism will utilize a drill and suction mechanism to collect dirt and deposit soil samples onto onboard test tubes. The test tubes on board the rover will support anhydrous testing for protein detection, and pH and nitrogen levels present in the soil samples will be analyzed using non-toxic indicators.
The software team this year has pivoted from ROS to ROS2, enabling the use of the updated nav2 package. Behavior trees and plugins within the nav2 package make the autonomy stack modular and allow us to quickly iterate. For odometry, we are combining wheel encoder as well as IMU and GPS from a vector nav sensor to accurately localize the robot. Additionally, we are using a Z2 stereo camera to provide depth data and detect Aruco tags. The Aruco tag detection package was custom built with the benefit of having many tunable parameters to adapt to different environments. Finally, custom navigation algorithms will be implemented for path planning and controlling motion, finalizing the autonomy stack.
Our rover will maintain communications with our operators using our base station and receiver antennas. The communication system runs on 900 MHz, 2.4 GHz, and 5 GHz bands. The 5 GHz band is used for high-speed video streaming for real-time control of the rover. The 2.4 GHz is used for general communication over mid-range distance, and the 900 MHz band is used for long-range communication with the rover for essential data. This ensures steady communication with our rover during the competition missions, even if it's out of direct line of sight of the base station antennas.
Moving forward, our team will employ further testing and validation for each of our rover's functions to assess our capabilities. We will implement mock missions to simulate the conditions encountered in Utah and assess our rover's performance and operator proficiency. We will continue to improve our rover's design to gear up for competition. Thank you for watching.